Here we've illustrated the light-dependent reactions of photosynthesis. And what we're looking at is we've got the thylakoid membrane here. And within the thylakoid membrane, we do have two photosystems. We've got Photosystem II embedded in the membrane. And then we have a very similar photosystem over here, which we're calling Photosystem I. And then right in the very center, the different colors, the pinks and reds, really orange, this is going to be an electron transport chain. It, again, is also embedded in that thylakoid membrane. So if we just go through and we talk about what specifically happens as we do have the light-dependent reactions occur. First off, light energy is going to come in and hopefully strike a pigment molecule. When the light strikes that pigment molecule, if that pigment is able to absorb that color of light, so if it's the right wavelength, we're going to take the energy and we are going to ultimately transfer it to the chlorophyll A pair. Now, as soon as the chlorophyll A pair receives that energy, we are going to excite an electron. So we will see an electron get boosted up in energy. And then the primary electron acceptor, shown here in aqua, is going to collect that electron. Once that happens, we have to replace the electron that just left from the chlorophyll A, and water from the thylakoid space or the thylakoid lumen is going to be picked up. It's going to be oxidized, and when it is oxidized, it turns into oxygen gas, and that will give the electron to chlorophyll A. So in that way, we're going to be replacing the electron that just left chlorophyll A. And this is going to continue in that we're going to have more and more light energy come in. And as that more and more light energy comes in and strikes the various pigments, we're going to continue to funnel the energy to the chlorophyll A pair, which means we're going to have to continue to oxidize water and replace the electrons. If we go back now and we talk about this electron, which we have collected in the primary electron acceptor, what is going to happen to that electron now is that it is going to get passed down an electron transport chain. So that would be right here. Now, as I've drawn it on here, I've tried to illustrate that the higher on the image we are, the more potential energy that we have. So as we pass that electron down the electron transport chain, with each one of these redox steps, a small amount of energy is going to be released from that electron. And as that small amount of energy is released, we want to be able to do something with that energy. So I just want to write up here first so that we can remember it, and so that it is emphasized that energy is released as the electron is passed down the electron transport chain. So that is the ETC. So this, I'm going to write it right here. That's my electron transport chain. So as that energy is released, that's going to be an exergonic reaction. And we want to take that energy and we want to do something with it. What is specifically going to happen with that energy is that we will be taking protons or hydrogen ions, which are the little pluses here, and we will be taking them from the stroma and we will be transporting them down here into the thylakoid lumen or the thylakoid space. Now, as I've illustrated it, we can see that up here in the stroma, we have a low hydrogen concentration compared to what we have down here in the lumen. So the lumen has a high hydrogen concentration. Since that is the case, this transport of hydrogens is going to be active transport. So this energy that we're releasing, that, if I just write it right here, we will use the energy for active transport of hydrogen. So in this way, we are going to be building up a hydrogen ion gradient. And hydrogen ion gradients are great ways to store energy. And what we will ultimately end up using that for is to power ATP synthesis by chemiosmosis. So we'll look at that in just a moment. Now, if we look at the other photosystem that we have over here, it would be behaving very similar to the first one, or Photosystem II, in that light energy is coming in. When light energy comes in, we take that energy and we pass it around until ultimately we do get it to the chlorophyll A pair. The chlorophyll A pair is going to excite an electron, which does get collected by a primary electron acceptor. This time, when we need to replace that electron that we've lost from the chlorophyll A molecules, we're going to take the electron that is now sitting at the bottom of the electron transport chain, and we're going to hand that or pass it to the chlorophyll A pair. So in that way, we do not actually oxidize a second water molecule over here in photosystem I. Now, if we go back to this electron that is excited and sitting in the primary electron acceptor, it is going to get passed just a couple of times, but ultimately an NADP plus molecule that is sitting in the stroma is going to come over here, it's going to collect that electron, and when it does, it turns into NADPH. And so NADPH is going to be holding on to that energized electron, and note that it is sitting in the stroma of the chloroplast. So those are the overall light-dependent reactions. The only part that we have not illustrated on here is that in addition to these complexes being in the thylakoid membrane, there's also going to be an ATP synthase enzyme located there. So I don't have a lot of room on this slide to illustrate it, but I'm going to draw right over the top of some of this that I have, just so that we can see that it is there. So if I were to put my ATP synthase enzyme in, and I'm just going to write it for now right on top of the electron transport chain, ATP synthase is going to be embedded in this membrane. Recall that ATP synthase is going to have a channel that the hydrogen ions can flow through, and then it also has this wheel on it. So as we build up this hydrogen ion gradient, we will have those hydrogens that will flow back through the ATP synthase. So let me just write on here that that is the enzyme that I've got. So the hydrogens flow back through, and that would be facilitated diffusion because they are now moving down their concentration gradient. And as soon as they do that, they are going to catalyze the synthesis of ATP up here. So with the active sites up here, those active sites will bind ADP plus phosphate, and they will actually be turning that into ATP. And that right there, that process is going to be chemiosmosis, very similar to what we saw during the third stage of cellular respiration. So what we saw during the oxidative phosphorylation, in that we have an ATP synthase, it's embedded in the membrane, and it's going to utilize the hydrogen ion gradient that we have so that we can actually power the synthesis of ATP.